Hello, this is Maureen Julian, and we are now starting Chapter 7, Part 1. The title of the chapter is Electron Density Maps. The theme for this chapter is the zebra, and that, if you notice, begins with the letter Z because we're at the end of our course, so that's why I put the zebra in. Now, the objectives that we're going to work on today will be the scattering by a single electron. Now, we're talking about X-rays, and X-rays are scattered by electrons, so we have to concentrate on the electrons. Now we assemble the electrons into an atom, and we look at that scattering, and we will produce, for the first homework exercise, first part of our homework exercise, the atomic scattering factor curves for specific atoms, and those atoms are going to be the atoms which are in your crystal. So if your crystal has carbon and oxygen and maybe an iron, then those are going to be the scattering curves which you will do. Now we take the atoms and we assemble them into a crystal, and from that we get the structure factors. And when we scattering of a crystal, remember, we get in a sense we get the reciprocal lattice superimposed with the intensities of the crystal. So that's what we're aiming at. And what we'll do, instead of calculating the entire contribution of all the atoms, we'll just calculate the contribution of one atom to the structure of your crystal. So let's start out by the scattering of a single electron. Here's our beam coming in. It hits the electron. The electron pulsates or radiates with the same frequency as the incoming beam, and it also the rays come off equally in all directions. So here is the atom scattered by an electron, and the scattering radiation has the same intensity in all directions. Now we take the electrons and we put them into an atom, and something else happens. Some of the electrons will have destructive or constructive interference. So we no longer get a same number intensity in all directions, but we do have cylindrical symmetry. The atomic scattering factor is known also as the atomic form factor, is actually the ratio of the amplitude of the wave scattered by an atom to the amplitude scattered by one electron. So we will see that at position 0, this is carbon. Carbon has 6 electrons, so it's adjusted so that the maximum here is at 6. This curve is calculated, and if you note it, and it's the Chromoman coefficients, we'll use that as our calculation. And if you notice, it has this unusual sine theta over lambda, which is Angstrom's inverse, as along the x-axis. We have the structure factor in electrons along the y-axis. And why do we have sine theta over lambda? Well, let's go back to Bragg's equation. Bragg's equation is n lambda equals 2d sine theta. We'll have n equal 1, and we can solve this for 1 over 2d. So we bring the 1 over 2d here, and we get sine theta over lambda on the left. Now, on the right, this is the 1 over 2d has to do with the specific crystal, and there will be isolated d spacings. On the left, this has to do with the experimental data, so this will be a continuous function. See this continuous function over here? So we want to build Bragg's law into our structure factor diagram. So that's why we use sine theta over lambda. When we're talking about specific crystals, we can take any point and do the 1 over 2d. Now each of the elements, and here for example will be copper at Z equal 29. Here's that copper curve, and that would come down like that. And hydrogen would be down here, oxygen would be at 8, carbon at 6, and we have all of the elements displayed up to 92. So let's look at the formula that we used, and this is essentially what your starter program will do. It will produce the scattering curve, and these coefficients are called the Kromer-Mann coefficients, and if you notice there are 4. You have 4 A's. A sub I goes from 1 to 4, B goes from 1 to 4, and there's 1 C. So we have 4, 4, 8. We have 9 coefficients. We're fitting the curve with 9 coefficients. So for example, for carbon, here are the 9 coefficients that we put into the Kromer-Mann formula up here, and we produce this, it's a function of sine theta over lambda. Here's the sine theta over lambda. And here's an example of Kromer-Mann coefficients for hydrogen, for helium, for lithium, and also hydrogen -1, etc. Now, I have done sucrose, for example, and for the homework that you had for last time, you calculated this curve, and what we're going to do is we're going to look at just the highest reflection. In this case, it's the 112, and here are the scattering curves. Sucrose has oxygen, carbon, and hydrogen in it. Here's the hydrogen starting at 1, the carbon starting at 6, and the oxygen starting at 8, and the here we have the 112 reflection, and the scattering of the oxygen would be, you could come back and look at that, that's about 6.8. The scattering of the carbon here is going to be about 4.5 or so, and the scattering from the hydrogen is going to be under 1. So about 0.8, say. In order to find where the position of this 112 reflection, we have to find out the sine theta over lambda, which of course is equal to 1 over 2d. So we need to calculate the 1 over 2d, or specifically the d, for the 112 reflection. Well, I've done that already for you. If you look back to Chapter 5, remember that starter program that was on the reciprocal lattice. That was the program when we superimposed the reciprocal cell over the cell from the direct lattice. And now you can go back to that program, and if you notice there was an H, K, and L that you could put in. So we put in the maximum reflection from your powder diffraction file, and we'll also need another little thing for later on. We might as well discuss that right now. We're going to select out an atom. So from the CIF file, so in this case I selected carbon 1, and here are the fractional coordinates, so I just put that right in there, and here are the fractional coordinates in the program. And remember, we calculated the G matrix, etc. Now, we had a series of little diagrams which were produced. This was figure 2, and you used the G and the G star, and now when you put in your highest reflection, you run that program again, you have it all set up, and here's your 112 reflection, and you'll see that the D spacing is 1.9343. I've calculated that for you. You take 1 over 2D, so 1 over 2 times 1.9, and that will give you the position along the curve. So here, this position is right here. That's the thing that we're calculating. Once we calculate that, we can come up and we can pick up the contributions to the 112 reflection of the oxygen, the carbon, and the hydrogen in the case of sucrose. Now that was the atom. Now we're going to put the atoms inside a crystal. Now when we put When we repeat the atoms in a periodic way, we get the lattice, and here is our reciprocal lattice. And what I want to point out to you, if you just look at this row, for example, here, you can see that the intensities of these spots are quite different. This is the most intense. The second one is here, the third one's here, and the fourth one, that's very, very faint, but if you look carefully, you can see it. Here's two, I've pulled out two reflections just so that they might look similar, but you can see they're really quite different. They have different intensities. And those intensities will tell you how the atoms in the cell diffracted or scattered, I should say, and that will allow you to understand what the structure was, and that's the whole story of X-rays, X-ray crystallography. So the structure factor depends on the type and the location. The type is it oxygen, is it hydrogen, and the location. What are the fractional coordinates? So knowing the type of atom and the fractional coordinates of each of the atoms in the unit cell, you can then calculate the structure factor, and then you can take the structure factor times its complex conjugate, and you get a number which is proportional to this intensity of the diffracted beam. So here is the structure factor. It has two contributions. The contribution of where is the atom, what is the atom. Where is the atom contributes to the phase angle, what is the atom contributes to the amplitude. And the atomic structuring factor is the total of all the atoms in the unit cell scattering together. So let's first look at the phase angle. For an atom J in a position R sub J, that would be, here's the fractional coordinates, and here's our bases A, B, and C. From that we can calculate the R, the distance of the atom from the origin. Then we have the particular reflection we're looking at, the HKL reflection, and that is going to be in terms of the A star, B star, C star, the reciprocal basis vectors, and their coefficients are called the H, K, and L. Now we take the dot product of these two vectors, and it's designed so that the A and A star equals 1, so we get this dot product is going to be the H, K, and L dotted into X, Y, and Z. And the phase angle in radians of the wave radiated from atom J is 2 pi times the H dot R. And let's look at a few examples. We have two places where we have a lot of zeros and everything cancels out. One is if H, K, and L are all 0. That is if we're looking straight ahead at the undeviated beam. So if H and K and L are all 0, then H is going to be all 0 because H, K, and L is going to be 0. So the whole phase angle is going to be 0. So the phase angle is 0 for all atoms that are scattering along the direction of the beam. Okay, another example would be, suppose we took the atom that was somewhere else if we took the atom at the origin and then we wanted to calculate the phase angle of that atom, then we again, the X, Y, and Z in this case are 0, 0, 0. The distance from the origin to the origin is 0. So when we do the dot product, we get 0, and the phase angle is 0 for any atom that happens to be at the origin. Now that's unusual. Those are two unusual cases. In general, what almost all the cases that we'll be looking at, the fractional coordinates are something like 0.2, 0.6, 0.1. There's some specific numbers, and the reflection we're looking at is, say, the 2, 1, 2. So now we just substitute in. So we have this, here's our formula. So the H, K, and L would be 2, 1, 2. So this is going to be 2, 1, 2. And the X, Y, Z are going to be 0.4, 0.6, 0.1. And there you can see it. And when you do that arithmetic, you get 1.6. And then the phase angle will be 2 pi times that, or 3.2 pi radians. And you're going to be doing that in your exercise. So now that was the position. Now what about the type of atom? Well, that's going to contribute to the amplitude of the structure factor. And again, we rewrite Bragg's equation in this form. And then we can look at the function, the scattering factor, which would be, in our case, the chromorman. And here is the calculation for hexamethylbenzene. And you can see here you have the H, K, and L. You can calculate the D spacing. We've done that in Chapter 6 and 5 with the reciprocal lattice. Oh, here are the examples here, and then we take 1 over 2D, and that will be what we're looking for along the chromorman diagram. So here is the scattering curve. Here's the 100 and the 010 extracted. So here is the 100, and you can see that the 1 over 2D is 0.06, so this is about 0.06 along here, and you come up and you read that for carbon at roughly 5.6 along here. Likewise, you could do it for the 010. Each one will be a little bit different, and in this case the 1 over 2D is 0.08, so that's a little further to the right here. And when that's further to the right, it's going to have a little bit lower scattering factor. So there's the 5.35. You can consider this, the D spacing 1 over 2D, of course, you can undo this and get back to the D spacing, you get 7.75. Now, if you take this function, you simply stuff it into the chromorman, you're going to actually get this long number out, but you can just read them off the curve here. That's quite good enough. Okay, now we're going to, in this final situation, we're going to put the whole story together. This is the formula for the structure factor. This is the part contributed by the atoms. This is the chromorman curves that you have done for each of the individual atoms. The J is over the atoms. And the position of the atoms, of course, contributes to the structure factor, and that is given by the phase angle. And finally, we have to sum it over of all of the atoms in the unit cell. But we're going to be doing that and looking at those equations for your crystal. So the second part of the exercise is going to be to calculate the number of electrons in the unit cell for your crystal. I've done it for sucrose, and we do it by means of this very nice little handy chart. So you have the atom at the top, you have carbon, hydrogen, and oxygen, however many you have in your particular crystal. And now we have the atomic number of each of these atoms. So 618, number of atoms, 12 carbons, 22 hydrogens, and 11 oxygens. You add all that up and you get a total of 45 atoms in the molecule. But we're interested in the scattering of the electrons, so we need to know how many electrons we've got. So we multiply the number of electrons in the individual atom times the number of atoms, and we get 72, 22, 88, and we add this all up and we get 182. So each molecule will scatter 182. Now, when you want to find out how many in the unit cell, we have to go to the CIF file and get the Z. The Z in the CIF file is 2, so that means that we have 2 molecules. So we have, where we had 12 atoms in one molecule, so we have 24 and 2, so that becomes, each of these numbers are 24, 44, and 22 for a total of 90. Notice, always check your math that the 45 and the 90 double each other. And you should do this in an Excel file, or I would do it that way. And now we have the number of electrons in the unit cell. So again, we multiply this number up by 2. So this is 144, 44, and 1. I'm sorry, you multiply the number of atoms times the number of electrons per atom, and you get for 144, 44, and 176, and you add all that together to get that the whole atom actually reflecting in the 0, 0, 0 position would all 364 electrons would contribute to the scattering. But of course, we're not going to see it in the direct beam because that gets hidden by the beam itself. And notice that this figure here, 182, the number of electrons in the molecule, that's going to be doubled here. So always just check these figures. Now, we're going to look at the contribution. Instead of summing it over everything, we're just going to look at the contribution from the highest reflection, which is 112, to the contribution of just one atom to it. But first of all, let's look here. Now we have this 1 over 2d. You know what 1 over 2, you know what d is from the starter program in Chapter 5, and you know have this diagram from the chart, starting with the structure with the starter program in this chapter, and now you can put that right on there yourself. And now we're going to do the calculation for sucrose. Let's look at the structure factor. This is the general equation. You just simply copy this down, and then you have to break it down into the number of elements. We have carbon, hydrogen, and oxygen. So we have a structure factor for carbon, for hydrogen, and for oxygen. For you, you'll have one structure factor for each of the elements that you have. Now we can just literally write out this formula up here. We can sum it over. We have 24 carbons, we have 44 hydrogens, and we have 22 oxygens. So to remind us how much is contributing to this structure factor, we rewrite this formula. And finally, we can write the formula out a little in more detail so we can be sure we understand it. And we have, again, here is the contribution from each of the positionals. And what we're going to do is we're just going to sample the contribution of one atom, and I took C1. You can take any atom from your particular molecule, and it could be the carbon, or it would be the hydrogen, or the oxygen in this case. And this shows you the fractional coordinates, and here I put the fractional coordinates here. Notice that I had you select an atom and put its fractional coordinates in when you were doing the starter program from Chapter 5, and you will get out now you can perform the answer here because you know what the scattering curve. You go to the carbon scattering curve, you pick off the 112 reflection, and you get 4.48, and then for the phase, you get here is this X, Y, and Z, and then you have the 221. I'm sorry, the 112. So this is times 1 times 1, and then here's the 2 from that 2, and then you perform this operation, and you can leave the pi in. Don't forget the I here because it's imaginary, and that is the contribution from this one atom, and that's the main calculation that I'm going to have you do. Well, let's review what we've done in this course. We have used crystallographic databases. Particularly, we focused on the Cambridge database. We certainly know all about the CIF file, the crystallographic information file. You've used that quite a bit through this course. You described the lattice mathematically with basis vectors, and we transformed between basis vectors. We calculated interatomic bond distances at angles using the metric matrix. We described rotational and mirror symmetry operations and their matrices. In Chapter 3, we worked on point groups, and we understood their relationships in the point group tree. Then point groups have to do with individual molecules. Now we put the molecules into a lattice. So we have, in the lattice, to study the lattice, we use the space group. To study the molecule, we use the point groups. And then we learned about the reciprocal lattice and its relationship to the direct lattice. You did a picture showing the superposition of one upon the other. You've done the powder diffraction file for your crystal, and each of the diffraction lines are solutions to Bragg equations. And finally, you calculate the scattering factor curves, and in doing each time, every time you're looking at your own crystal, you're interpreting the published crystallographic data. That's all, folks. Bye.